Swayam Prabha. Digital India. Educated India.
Let's then go to Shor's algorithm. Okay, so what we'll do is we'll first consider the simplified case. Okay, so where I'm going to say that let Q be some sufficiently large number. So let's say that Q is much greater than even n squared, where capital N is what we are trying to factor. Okay, and let's assume that the order of the element, right? So Shor's algorithm is going to let us compute order x, right, which is what we wanted according to the previous theory that we developed. So I am going to assume that R in fact divides Q. So this is what I was saying, that I will not in fact show you everything that I need to, because this is a pretty bad assumption. I mean, it is an unjustified assumption. The idea would be that we will see how it works in this case, and then if I remove this assumption, then turns out that there is a bunch of complexity that comes up, but all of it can be handled by using, I mean, the broad outline will still stay the same. We just need to handle, instead of getting integers, we'll get fractions which we'll need to round and so on. Okay, so we'll not go too much into that. So we're just going to make this simplified assumption and first see the algorithm. Okay, and yeah, I leave it as a reading exercise to sort of study the more general case where we don't make this assumption. Okay. So for the case where we assume that R divides Q, by the way, here note, just think about what we are doing, right? So we have this we have this n that we want to factor, and what we are doing is we are sort of trying to find the order of an element x, which we were denoting by R. And we saw that finding the order of this element is sufficient for us. So here we have no real way of knowing how to pick Q. This is what I'm sort of emphasizing, that actually we don't know how to pick Q, but we'll just choose some large Q which will be sufficient for us, and as I said already, we'll consider these cases separately. Okay, so yeah, I just wanted to emphasize that we really don't know how to pick Q. We'll just pick something and hope for the best. So the algorithm itself is very simple to similar to what we have seen already. So you start with registers 0 tensor 0. Okay, so here this could be sufficiently long. Okay. And now what you do is you prepare the superposition over all inputs by applying the Hadamard. Okay, so far this is standard. right. So, we took our initial 0 registers, we applied the Hadamard transform to get to get the superposition over all inputs. And now now we need to define a function that we care about, right. So, let us define f of a as x to the a mod n. Okay, so this x is chosen uniformly, right. And yeah, so we want to find the order. So, now note that f is distinct on 0 to r minus 1. Okay, so remember that the order x is denoted by r. Okay. So, now we will apply our function oracle as usual for this function. Now, who can tell me what we should do next? So, measure the second register. Good. Okay, so when we measure the second register, as we have seen, all the input values that are inconsistent with the measured value, these will disappear, right, and we will renormalize. So, what we will end up with is something like this. So, you can convince yourselves that this is the right normalization factor. Okay, so I am just using L as the some sort of some characteristic value which gives us a fixed f of L. Okay, so now what we got is we got this superposition over all these inputs that are consistent with a given f of L value. Now, in general, what do we do at this point? We just throw away the second register, we do not care about that anymore. Now, can I measure? So, yeah, we cannot measure at this point because every time we measure we will get a different L, right. So, we will not get anything consistent. So, instead what we will now do is apply the QFT, yeah. So, apply QFT. And the very important thing is that this drops L, right. So, we talked about this quite a lot while doing Simon's algorithm, that it becomes independent of the color. So good. So having applied the QFT, what am I going to get? I am going to get something like this, 1 over square root r summation k equal to 0 r minus 1 omega to the KL, okay, k q over r. Okay, so this is just the QFT. Here I am directly writing the points on which I am going to get non-zero probability. So when we did Simon's algorithm over Zn, we spent a lot of time arguing why once you apply the QFT, all your probability will be concentrated on points that look like this, right? So let's not do it again. So yeah, so we are just saying now that, well, QFT looks like this. So this is just a normalization factor, this 1 over square root r, anyone can compute and see what normalization you should get. Omega to the KL is the Fourier coefficients, and these points follow by the analysis that we had done last time. Okay, so we get something like this, and that's it, right? So now we measure. So now that we measure, we are going to get some KQ over R. Now remember that we assumed that R divides Q. In this case we assumed that. You can also check that GCD of K and Q over R is going to be 1 with good probability. So I am not proving this again, I am just sort of saying it. Okay. So then computing the GCD of Q with KQ over R should give us Q over R. Okay, and this in turn gives us R because we know Q. Yeah, so it's the same idea that we have seen before, and yeah, as I was joking at the beginning of class, I am in fact cheating here, because what I am showing you is the simplified analysis, when we assume that R divides Q. In that case, actually the algorithm and the analysis becomes extremely similar to this Simon's over Zn, which we already did. The more complicated case is, when the function is almost periodic. So, when R does not divide Q. In that case, what we will need to do is, talk about points that look like this, right? So we have to worry about rounding and whether the analysis works out and so on. So I spent a lot of time actually thinking about what is the best way to present this algorithm. Obviously Shor's algorithm is sort of like a grand finale for us in this course, intermediate at least. But in the end I decided that going into all of the involved analysis that handles these issues, I feel is worthwhile, but maybe not in class. So it is something which I encourage you to read offline. I will just make a few remarks about it here, but I feel that the idea of the algorithm is perhaps best understood by looking at the simplified case. Okay, so the additional care that we need in the general case is something that is yeah, it's something that I think is better read offline than for us to do it in class. So I will, as I said, talk a little bit about the general case, just to give some intuition. But are there any questions about what we have done so far? So remember, we started by looking at discrete log and factoring. We said that discrete log reduces to period finding. We said that factoring reduces to order finding. We did this in some steps, right? Finding a non-trivial square root of 1 mod n and then finding an order which will give us a non-trivial square root of 1 mod n, and then we developed this algorithm to find the order. So the algorithm is quite similar to the algorithm that we saw last time, right? And yeah, it's this, that you prepare the input superposition, right? You apply the function oracle. The function is x to the a mod n, right? You're trying to find the order of x, and then you measure and you apply QFT, and you measure again, and you analyze and show that you will get multiples of Q over R, which knowing Q allow you to recover R. So this is just the idea. Okay, so this is Shor's. So let me just say a few words, like I promised, about the general case. So yeah, so need to analyze points like kq over r rounded, right, and can show that we get constructive interference at points that are close to multiples of Q over R. Okay, and basically what we can show is that if you simply round Q over R to the nearest integer multiple, then that suffices to recover R with some probability. So there is some care required. You have to look at continued fractions and so on. But yeah, like I said, I felt it would not be worthwhile for us to spend too much class time on this. So yeah, this is the order finding algorithm, which in turn gives us factoring and yeah, also discrete log. Alright, so we'll end class here today.